Okay, welcome to Chapter 13, Part 3. In this lecture, I'm going to be talking about a particular example of a linear regression analysis, and then at the end, we'll talk about outliers and influential points. So our data set, or our example we're going to consider in this lecture, is the Song of Insects. It comes from the book The Song of Insects by George W. Pierce. This is from 1948. And Pierce mechanically measured the frequency, or the number of wing vibrations per second, of chirps, which are pulses of sound, made by a striped ground cricket at various ground temperatures. Since crickets are ectotherms, which means they're cold-blooded, the rate of their physiological processes and their overall metabolism are influenced by temperature. Consequently, there is a reason to believe that temperature would have a profound effect on aspects of their behavior, such as chirp frequency. And in general, it was found that crickets did not sing at temperatures colder than 60 degrees Fahrenheit or warmer than 100 degrees Fahrenheit. So as we approach this problem, the first thing we should think about is a theory. And elements of the theory are outlined in this description. But again, I think we can be a little more specific about the theory. Now, the first part of the theory is that the frequency of chirps is related to the temperature, okay? So that's part of the theory. But I think since these crickets are cold-blooded, that we might be able to be more specific and say that not only are the number of chirps related to temperature, but the number of chirps, or the frequency of chirps, that the frequency of chirps increases. And since we're doing linear regression, I'm going to add increases linearly. As temperature increases. Oops. So this is our theory. Now, even more specifically, if I define variables, say I make y frequency of chirps, oops, and x temperature, then theoretically there's if I can measure all the crickets out there in the population and subject them to this test, then there would be some theoretical model, and that would translate to the null and alternate, because remember, the null and alternate aren't about the data set, they're about the whole population. The null is there's no slope. The slope is zero, meaning there's no relationship. And then since we're saying positive linear here, we're going to say that beta is greater than zero in the alternate. And from the last lecture, you should now see that we could also define our null and alternate in terms of rho, the population's correlation coefficient. But again, our focus is going to be on beta, which is the rate of change of the frequency of chirps as the temperature changes. So that's our theory. Now, let's take a look at a data set. So again, remember I made y the chirps per second and temperature x. And that's because I think it makes sense to view the temperature as independent of chirps. And in fact, what we're really saying in this theory is that chirps increase as temperature increases. So the y variable is going to be dependent on the x variable. And again, y is the traditional variable for the dependent variable, and x is the traditional variable for the independent variable. And another way to think about this, though, is this is the prediction, and this is the predictor variable. Or we also, sometimes we think about the prediction as the response, and the predictor as the explanatory. Okay, now we're going to do the full regression analysis here. And so first thing we need to do is enter this data set into our calculator. So let me bring up my calculator, and let's see, I want to be able to see the data here at the same time. Okay, so there we go. So let's review how to enter a name list into the calculator. First thing I want to do is go to the data editor. So I'm going to press Stat, choose Edit. This takes me into the data editor. So now I'm going to move my cursor all the way to the top, and I'm going to insert a blank list by pressing second delete. Notice it inserts always to the left. And let's see, let's name this chirp. So I press down arrow again, and I can start entering the data now. Oops, I see a mistake. That must be a mistake. 416.3. Let's see, I think that was supposed to be 15.4. And 16.3. Okay. So now I'll arrow to the right, all the way back to the top here for L1. Second, insert the next list. And this is the temperature data list. Oops. So I'll call it temp, and I'm going to put a C for temperature for the, and I might have multiple temperature data sets, so I'm going to put the C on the end to remember that this is the temperature for the chirp data set. Okay. And I'll enter the temperature data into this list. And I'm going to go back through the data one more time to look for errors. I'll go from the bottom to the top this time. Okay, all that looks like I entered all those values correctly. So first thing I want to do on the calculator is look at a scatter plot. So let's review how to draw a statistical plot on the calculator. The 3 steps are enter the data. We just did that. Second step is to configure the stat plot window. So I'll press second y equals to take us to the stat plot menu. Then I'm going to choose plot 1. It's on. Choose the scatter plot icon, and then we need to cut and paste these lists in here. And I already have the right lists in here, but let me just demonstrate. I'll clear those out and assume that I had the wrong lists in. So I would just clear out the list and then go second stat, and I need to scroll to the temperature data. Okay, so I'll cut and paste the temperature data in there, and then clear that out, pretend like I had the wrong list in there, and then we'll put the chirp data there. Second stat, and then go down and find the chirp data set. Okay, it looks good. So that's the second step complete. Then the third step is to set up the scaling for the axes. And scatter plots work really well with a feature called zoom stat. So if we press the zoom button and then we go down to choice number 9, and these are all different zoom windows that the calculator can draw, but zoom stat will set up an appropriate window for a scatter plot. And when I look at the pattern here, I definitely see what looks like a positive increasing pattern here in the data set. And that's a good thing because that is the first piece of the puzzle as I go to do this analysis, okay? So let's take a look at where we're at so far, okay? So, null hypothesis, beta equals 0. Alternate hypothesis, beta greater than 0. We're waiting for a p-value, okay? So we're going to find the p-value on the calculator. But for now, the alternates looks good because the scatter plot shows a positive linear trend, okay? And so that scatter plot's giving us a confirmation that we're working with the right theory. But we definitely want to look at a p-value, okay? Because the p-value is going to be kind of where the rubber meets the road here and tell us whether or not our relationship's statistically significant. So let me go back to the calculator for a minute here. I got quite a few open windows there. All right, now, so we just looked at a scatter plot on the calculator. Looks good. Now I'm going to go and do the Lin-Reg t-test. And Lin-Reg t-test is where I'm going to get a p-value. That's where I'm going to get A and B for the best fit line for the data. It's where I'm going to get R and R squared. So all of those pieces of the puzzle that we need to look at for a regression analysis, or many of those pieces of the puzzle, can be found under or by using Lin-Reg t-test. So I'm going to go stat, and I'm going to go over to test this time because Lin-Reg t-test is a statistical hypothesis test. So I scroll down through the options and looking for Lin-Reg t-test. Oh, looks like I went one too many. Linear regression t-test. Okay, I'll choose that. And again, I need to enter the correct X list and Y list. And I just pressed vars, which is the wrong, that was the wrong thing to do. So there's no go back button on the calculator, unfortunately. So I got to go back to stat, back to tests, and back to Lin-Reg t-test. So as they say, stuff happens, right? Okay, so All right, what I meant to press is the clear key. So assume that there were no, so I'm going to assume that there are no data lists here. And what I'm going to do is insert one in. I just press clear, so I'm going to go second stat, and I'll go down and find the chirp data set. And this is how I paste that right into the, oh no, that was the wrong one. Needed temperature. XList is temperature. So I'll go second stat and find the temperature data. Okay, and then chirp is the Y list. So I won't bother to change chirp. I'll assume you guys are getting a handle on this now. So theory is, now notice here, beta and rho, the calculator is going to do the test for both beta and for rho. And our theory is that there's a positive linear relationship, so we want to move the cursor over here to the greater than 0 option and press enter. And this time I'm going to have the calculator save the best fit line. I already have Y1 in here, but let me clear that out because it's possible that you may already have had when you're looking at your computer or calculator screen, you may see Y1 there. Just leave it there if that's the case. If there's nothing there, go to vars and then arrow to the right to yvars and choose function, and then you can choose Y1. What the calculator will do by putting Y1 here is automatically paste the best fit line, the equation of the best fit line into Y1. And now I'm going to press calculate. All right, so first thing that catches my eye is the p-value, 5.9730, etc., times 10 to the negative fifth. So oh boy, is that, let's see, every time I go between this and the calculator, I'm realizing I think it erases what I've written. The p-value is about, what do we say, 5.9 times, so I'm going to call it about 1, 2, 3, 4, 5 zeros, and then I'll round that 5 up to a 6. So that's a small, very small p-value. This means we should reject the null. That beta is equal to 0, and accept the alternate that beta is greater than 0. And the conclusion based on this p-value, the data, we would say the data is statistically significant, and there's evidence of a statistically significant linear relationship. And this is also confirmed by the pattern in the scatter plot. So the pieces of the puzzle are coming together here, okay? Now, next number that we want to look at or consider is r squared. And we can look at r at the same time. Now, as I scroll down here, okay, I'm going by a and b, okay, and again, look at the calculator at the very top here. It shows the form of the model, y equal a plus bx. So the slope is b, a is the constant, here are the values a and b. But I want to focus on r squared for a minute. So r squared, this is the coefficient of determination. It's about 0.69. So what we would say Okay, so r squared is about 0.69. Okay, and this is what we call the coefficient of determination. So how do we interpret this? What we say is approximately 69% of the variation in the frequency of chirps is explained by the temperature using a linear model. And again, I'm using that word model again, but the idea here is the linear model is the y equal alpha plus beta x, or the y equal beta x plus alpha, depending on which way you decide to write that equation. But in any case, this is the correct interpretation of r squared. Now, I want to say a couple other words here about r squared. Now, we're saying, or r squared is telling us that 69% of the variation in the frequency of chirps is attributable to temperature. But notice that leaves 21% unexplained. Now, this is, we're doing univariate stats, okay? So we won't consider the multivariate situation. But I do like to mention it because what the 21% is related to are other variables that might be out there that also explain the chirping. In other words, or the frequency of chirps. So if you think about it for a second, temperature is one factor here, but there are other factors. It could be it could be a genetic thing. Some crickets might be particular quick crickets are probably more into chirping than other crickets. So the idea here is that a lot of the variation is related to temperature. And in fact, the fact that r squared is 69% tells me that temperature is probably the most important variable. But that's not to say there aren't other variables also that are important in terms of, or that influence what the frequency of chirping is for crickets. So this is not the only story. Okay, so let's go back to the calculator here for a second and see what other numbers we can look at. So let's look at A and B. So A is about 0.46. I'll round that to the nearest hundredth, and B is about 0.20. So the equation of the best fit line, I already forgot those numbers. Let me remind myself what they were. So A is 0.46, B is 0.2. And I'm going to put a y hat on this because this is the model that comes from data. So remember, we have y hat equal bx plus a. And again, I should make a note. You can write this equation as either bx plus a or a plus bx, and that's because addition's commutative, but it's the same equation either way. So this is useful for predicting chirps or predicting the frequency. So, for example, if the temperature is, say, 80 degrees, then our prediction for the frequency it chirps would be 0.2 times 80 plus 0.46. 0.2 is 1/5, so this is, and I should use an approximation here because I rounded these numbers off. Let's see, 16 plus 0.46. So we're talking about 16.5 chirps is our prediction. Now, let's look at this in a different way, though. Let's look at this graphically. Okay, so I just used the equation to make that prediction. But now if I go back to the calculator, okay, remember we elected the option of having the calculator automatically store the equation into y1, and it's showing more accuracy. The calculator's not rounding to the 100th place like I did. If I press graph now, what I'll see is the graph going through the data. Graph, that line looks like it goes through the data pretty well. And I'm going to do a trace. Okay, right now the calculator's tracing on the points, but I want to get on the best fit line, so I'll do a down arrow. Now the calculator's tracing on that line. So what I can do is put in, remember I did a prediction for 80 degrees, so I'm going to go and now just type 80. Notice the calculator pops up an x equal. I type in 80, press enter, and the calculator takes me straight to that point. 16.69 is what the calculator is getting. And again, I have some round off error in my calculation because I didn't carry this much accuracy. Generally speaking, it's good to look at, to go ahead and let the calculator do all these computations, because typically the calculator doesn't round as, or uses more precise values, doesn't round like I did. It has to, I mean, of course the calculator has to round, but the idea here is that there are many more decimals of accuracy on the calculator. Okay, so that's how we would make a prediction using the line. What else do we have? Let me go back to the, let's see, I'll go back to the home screen now. Unfortunately, when I go to the graph and back and forth, I lose what was on the screen, so I have to go back and do the linreg t-test over so I can see make those numbers active again. And the other number that is useful, or we should take a look at, is R. Now remember, R is the correlation coefficient. There's two things we can tell from the correlation. First is if the sign is positive, it means that there's a positive association, which is what we're seeing in our data and our p-value, or the hypothesis we tested was that beta was greater than 0. We got a small p-value, rejected the null. So again, the R value of 0.8 fits into the puzzle we're putting together. And the fact that it's about 0.8 means it's a pretty strong correlation between the variables. Now there's another kind of analysis that I want to demonstrate with this example as well, and it's called residual analysis. So let me take a moment and talk about residual, the residuals and residual analysis. Okay, so I'm going to do a couple of quick sketches here just to make a point. Okay, so I'm not going to bother to scale the my axes now. I'm just kind of talking about this generically. All right, so here's the line, and suppose that I have a few points. I'm not going to go crazy here. I'll just put a few points around the line. And what I'd like you to remember is that the distances between the observed values, which are the points, and the predicted values, which are the corresponding y values on the line, those differences are what we call the residuals. And sometimes we notate that with an E, and the E comes from error. So E sub I is going to be the Y sub I, the observed value, minus Y hat sub I, which is the predicted value. So remember, each one of these points, these 2 points, has 2 coordinates, x1, y1 for the observation, and x1, y hat 1 for the prediction. And again, notice if I go down here to the x-axis, this particular value on the axis is the x1 value I'm talking about. This particular value on the y-axis is the y1. And of course, the predicted value, y hat, comes from the best fit line. By plugging in that x value into this equation, we get the y value out of the equation. Okay, so the residual is the difference between the observed value and the predicted value. So in the scatter plot I just showed you, what we can do is look at a different graph, okay, which is going to be x versus, now instead of y, we're going to look at the residuals, okay? So and I guess I should have made that, I put a dash line in here. That could have just been my x-axis, actually. I'm kind of regretting not drawing it that way. But actually, how am I going to fix this? Let me just move the x-axis up to here. And the reason I want the x-axis kind of up here in the middle like that is because the residuals are going to be, some of them are positive, which means they're going to be above the x-axis, and some of them are negative, which means they're going to be below. And of course, the x-axis is the y equals 0 line. So this is the better way to draw the axis. Okay, now the residual for this point is going to be negative because the observed value is below the line. So if I take y minus y hat here, y is going to be smaller than y hat, so the difference is going to be negative, and that's going to give me a point down here. If I'm looking at, again, I'm looking at this point down here on the residual plot, and what I'm drawing, or what I'm graphing, are these distances. So this distance here is positive, so that residual would be positive. This one's negative, so that one would be negative and bigger than this one. And then this one is positive up here, and then this one's also positive. So that residual plot from this hypothetical example would look pretty well scattered randomly. And key thing here is there's no pattern. There's no pattern in the residual. And no pattern implies linear model is appropriate, is the appropriate model, okay? So what's another situation we might have? Well, let's take a look at another situation we might have. And actually, let me remove the clutter here and look at this in a different possible scenario. So I'll draw x and y axis again. And this time, let's say we've got a situation where I drew too many data values, more than I need, but that's okay. Notice that in this case, what we were seeing is a flaring out of the data from left to right, okay? And again, this line right here that I just messed up, that's the line corresponding to the model. And what would the residual plots look like? The residual plot look like here? Well, this is the residuals, not the y value now on the y-axis. So in this area down to the left, what we would see are these residual distances would be relatively close to the x-axis. And then as we move away, those points start to flare out. And so again, what I'm looking at are these vertical distances, and the vertical distances would plot up, and that flaring of those increase, the increase in the magnitude of the residuals is what we call a trumpet shaped residual plot. And what this tells me is that the variation in y, and these are the observed y's, is increasing. So one of the assumptions with regression modeling is that, let me get this written down. So the trumpet-shaped residual plot tells us the variation in y is increasing as x increases. And what that's going to do is that's going to tell me there will be more error in predictions because there's more variability on the right than there is on the left. So we have to be careful about this. We need to proceed with caution and perhaps do some transformations, but that would be an advanced kind of an idea. Okay, so let's look at one other possibility. Okay, another possibility for the residual plot might look like this. Again, just drawing a generic XY coordinate system and talking about just a generic situation. Now, it could be, and again, this line I just drew is our Y hat line. Okay, this is the line of best fit. And suppose we had a situation where our data values started on one side of the line, dropped below, and then came back over to the other side. Okay, and again, when we look at these residuals, the ones on the left are positive, the ones on the right are going to be negative, and so on. What the residual plot does is it magnifies this pattern. Oops, doggone it. Oh man, look at that. Shoot. All right, let me redraw that real quick. So the idea here is that we have a situation where the points start out above the line, go dip below, and then come back out above the line again. And that pattern is going to be magnified when we look at the residual plot. So we'll have one here, 3 like this, and then 2 above. And this is a curvilinear pattern. And what this implies that a nonlinear model is more appropriate. And we have some techniques we can use to deal with this. And I'll do a lecture down the road, or one of the next lectures I'll do on Chapter 13 will be dealing with the curvilinear pattern in the residuals. So when I go back and take a look at the actual data set we've been analyzing, which is the chirps and temperature data set, then what we can do is look at a residual plot on the calculator. Now, every time you do a linear regression t-test, the calculator will automatically store the residuals, okay? Automatically. And if I go second stat right now and look at my lists, okay, and I scroll down through the lists here, and you'll have this list as well on your calculator if you've done a linear regression t-test. There's a list called resid. And the calculator automatically creates this list. And then every time you do a linear regression t-test, the calculator automatically calculates all the residuals and stores them in this list. So to create the residual plot for this situation, here's what I need to do. All right, I'm going to go second y equals. Oops, I didn't go. I just went y equals there. I guess I pressed second twice, but that's okay because I want to clear this equation out of y1 anyway. The best fit line is not relevant for the residual plot. All right, so we're drawing a stat plot. First thing I'm going to do is enter the data, but that's already happened. The calculator did that automatically. So I'm going to go second y equals to the stat plot menu, choose plot 1, make sure it's on. This is also a scatter plot. Now, we always leave the X list as the data set for the X list. What we change is the Y list from, in this case, the chirp data. And what I'm going to put in here is the residual list. So I just press second stat. I'm going to go and find the resid list and paste that list in as the Y list. So the scatter plot I'm going to look at to do a residual analysis is the plot temperature versus residuals. And again, I need to rescale the window. So I'm going to do a zoom. Shortcut is just to press 9, zoom 9. All right, so when I look at this scatter plot for the residuals, it actually looks pretty good. Now, you might say, yeah, it looks like there's a little bit of a curvilinear pattern here, but that's not a very distinct pattern, I don't think. It's pretty random. So I wouldn't necessarily be looking for a nonlinear model here in this example. I think this residual plot's telling us the linear model is a pretty good model. Okay, now let's move on to this idea of an outlier or an influential point. So what I've done is I've added a point to the data set in red here. And what's going to happen here, what's really happening is we're seeing a 91.8 degree temperature and only 9.2 for a frequency of chirps. Now, that seems like a pretty low number for that high of a temperature when I look at the rest of the data. So what we're going to do is incorporate this into the data set, this particular point, and see what effect it has. Okay, so I'm going to go to my calculator. And I'm going to go to the list editor. And what did I have here? I already forgot. 9.2, 91.8. So I just added that erroneous point, okay? And I'm going to redo all of the analysis and see what happens, okay? So let's do the scatter plot first. Second stat plot. Now I got the temperature resid window configured, so what I want to do is, and actually what I can do is, I'm going to turn this window off, or this plot off. And notice I just arrowed up to the top and I can toggle to plot 2. So I'm going to actually go ahead and use plot 2 for this next one. And I'll turn it on and it's going to be a scatter plot. And I'm going to change the X list to temperature, second stat. Find the temperature data set. And the Y list are chirps, so get rid of L2 there, and I'll put chirp in here. And incidentally, as a shortcut, I could go alpha C, and this will skip me down to the C's. All right, now zoom 9, because I need to rescale the axis. So Now what I'm seeing is this point down here is far away from all these other points, okay? So this point down here is going to have a dramatic effect on the actual analysis. And just to see how much of an effect or how influential that unusual point is, what we'll do is do our Lin-Reg t-test again on this modified data set. Okay, everything stays the same. And lo and behold, our p-value is no longer significant. That means I'm not able to reject the null hypothesis. And r squared is only 4%. So that one data point has had a profound effect on our analysis. And it's actually pulled this line down towards it. And that's what influential points do. And in fact, we call those points leverage points sometimes. And what's actually happening here, I can demonstrate like this, okay? So, whoops. Let me see if I can draw a better line than that. So, with the original data set, okay, I'll just kind of sketch it out here roughly. With the original data set, things look pretty good. When we introduce that unusual value, the effect it had is actually pulling the line down towards it. And just by adding that one point, it leveraged the line down towards it, pulled it down towards it. And that's why we call it influential. So this point is a leverage point because the x values are actually within the range of x values, but it's an unusually small or low number of chirps. Now, in this situation, if I were a statistician and I were analyzing this data set, I would want to investigate this number, okay? And the first thing I'd be asking is this a mistake? Okay. Fortunately, there is no unusual data set or data value in this data set because it's from 1948. So I'd have a pretty hard time tracking down the person that collected the data and asking them the question, did you make a mistake here? Because it looks like it could be 19.2. So I'd be very suspicious about this. These influential leverage points can be a real problem for our analysis, especially if we don't have the ability to track down the person that actually collected the data and documented the data. Because it could be that the data value was correct and that one chirping cricket was messed up somehow and it just threw all of our results off. So the definition of an outlier is an observation that has a residual that's unusually large. An influential point is an observation that has a great deal of influence in determining the regression equation. Removing an influential point would markedly change the position of the regression line. Okay, and so I can demonstrate that idea by going back to the calculator, okay? And what I'm going to do is, and now remember, this point down here is that leverage point, okay? And so in y1, I just press y1, I'm going to leave that equation in y1. What I'm going to do this time is I'm going to go back to the data set and I'm going to take that introduced point out. I'm going to take that unusual point or that influential point out, and I'll do the regression analysis one more time, okay, on the original data set. All right, and this time what I'm going to do is I'm going to have the calculator store. I'm going to get rid of y1 here. I'm going to, oops, yeah, I'll go vars and then yvars and function. And this time I'm going to put y2 in there. This way I'll have both the original regression line, or I'm sorry, I'll have both regression lines, the one with the influential point and the one without. And let's see, if I do, I believe now if I do a zoom 9, I'll be looking at the original scatter plot. Now, the line that the calculator drew first is the regression line with the outlier, and then the second line that came in was the original best fit line. So you can see that one point had a dramatic effect on the position of the regression line. By having that outlier in, it leveraged the line or pulled the line down towards it. All right, so that's it for this lecture, and I'll be making another lecture as well, maybe 2 more lectures on Chapter 13. So this is the 3rd lecture in the series. I hope things are going well.